So we're going to need to log into Jasper and then to node CL2 and 230, where our test cluster is. If you haven't been here yesterday, you're going to have to copy over that working directory. If you have copied it over, you're going to just have to cd into the scheduling directory that you've already copied over. So inside there, or if you follow the link in the slides here, if you type this out, you could get to the workshop scheduling presentations, and then in there you'll see a number of things. You'll see the worksheet. You'll see something called PBS script, which is a reference to all the PBS commands when we're submitting jobs. And you'll see third one, scheduler commands. And in here, these are the commands that we send to the scheduler to see what's going on the scheduler. So, it's yesterday's course. Here, sorry, today. Okay. Is everybody in on the test cluster there on node CL2 and 230? Is anybody having a problem? If you are, you could speak up, or you can send a message. If you want, you could also send a message acknowledging that everything is fine. After we get a few, we'll continue. Okay. So we're going to be doing scheduling and job management part 2, how to use a cluster effectively. So in this, we're basically going to have a second part of job submission, as well as understanding jobs. So a big part of job submission is memory. PBS jobs in memory. So it's very important to specify memory correctly. If you don't ask for enough memory and your job uses more, your job will be killed. If you ask for too much, it'll take much longer time to schedule your job, and you will be wasting resources. In addition, you could be charged for it, in the accounting sense and in your priority sense. If you ask for more memory than is available on a cluster, your job will never run. So you have to make sure that you ask for a reasonable amount that can run on the cluster that you're asking for. So the scheduling system will not stop you from submitting a job and will not even warn you. So if you ask for 20 terabytes of RAM with your job, there is no machine like that on this cluster. Your job will never run. It will always be optimistically looking until we install such a machine on this cluster, such a server. But that's not going to happen. So if you don't know how much memory your jobs will need, you need to ask for a larger amount in your first job, then run check job minus v in your job ID, or do a qstat minus f, or look at the output of the email that is sent when you run the first job. And in there, it'll specify how much memory was used. Then on your subsequent jobs, you will know roughly how to estimate and put it in. So this is the way we handle memory. A few tips about it. Always ask for slightly less than the total memory on a node, as some memory is used by the operating system, and your job will not start until enough memory is available. So if there is 48 terabytes of memory on a cluster node, or 24 terabytes of memory on a cluster node, if you ask for all of it, the system won't have all of it available because some will be used by the operating system. So one good way of asking is, instead of asking for actually 24 gigabytes, ask for 24,000 megabytes. Because there's slightly more than 1,000 megabytes. There's 1,024 megabytes in each gigabyte. So if you ask for 24,000 megabytes, that'll leave 144 megabytes for the operating system. So you can ask that way. If you don't, your job will never run. Although there's enough space, there's not enough space after the file system after the operating system takes some memory. So are there any questions? Okay. So you can ask for memory in two ways. You could ask for it directly in your job. So you could ask for 24,000 megabytes with a PBS minus L mem. Or you could ask for amount of memory per process. So say you're running an MPI job with 50 cores. You could ask for 2,000 megabytes for each core. This way, you could quite easily change the number of cores you're using without actually having to constantly do the calculation for the memory. Any questions? So we'll go on for some more advanced topic here, features and partitions. So sometimes nodes have certain properties. Sometimes they have a fast processor, a bigger disk, a solid-state disk, a fast connection, or belong to a certain research group. Such nodes can be given a feature name by a sysadmin, so you can ask for the nodes by the feature name in your PBS script. So if we had SSD disks, solid-state disks on Jasper, we could have created a feature for nodes that had it, if we only had it on some nodes. And then you could ask for nodes with that feature. So that's often used on some clusters. We don't use that on Jasper, but there are clusters in Compute Canada which do use features, as well as certain research groups may have your campus cluster and so on. Another idea is partitions. So partitions are sets of nodes that you could specify for your job, and your job must run with all of its components inside a partition. So for instance, on Orsnes, the machine at UBC, the WestGrid machine there, they have a newer partition called QDR. So they have two switches, one fast switch, one newer switch, and one slower switch. And the connection between those switches is not as fast as the connections on each switch within each switch. So a partition would be used for this. Your job would run it either in one partition or the other. But there wouldn't be enough switch bandwidth to have your job cross those switches, right? Because that would take too many connections between those switches. There's not enough bandwidth there for your job to run. So that's how you use partitions. On Jasper, there is actually basically two. That does happen. We utilize another way of doing it with node sets. But basically, we stop your job. Your job can run either on the new nodes or the old nodes, but will not run on new nodes and old nodes. On Jasper, you can't actually ask for which nodes your job will run on. On Orsnes, you can, and you use this partition feature. Any questions? So PBS jobs and GPUs. You could request GPUs. Oh, okay. I have a question. How do we know when to partition? So you usually don't have to know. I mean, you don't have to know when to use a partition, or you don't. Usually, these systems are set up that you don't need to specify a partition. You only specify a partition if you need to do something in particular. So for instance, on Orsonus, if you wanted to force your job to run only on the newer nodes, which means that even if the older nodes were available, your job would not be scheduled there. If you wanted to enforce only run on the newer nodes, you would then select it and use the partition one. So this information would be found on the WestGrid webpage for Orsonus. And the same thing for other machines out there. Any other questions? Okay. So PBS jobs and GPUs. So GPUs are another resource. And just like you have nodes equals 2 processors per node equals 4, which means 2 nodes with 4 processors per node. You can also have a colon GPUs equals 3. In this notation, you are asking for 2 nodes with 3 GPUs and 4 processors on each node. So 6 GPUs, 8 processors, half on one node, half on the other. And the modern torque program recognizes GPUs and the state of the GPUs. So it will prevent, if you only have 3 GPUs or on a node, it will prevent more than one person running GPUs, or more than 3 people, more than 3 GPUs being used on that node at the same time. So what's a GPU? So that's a graphics card. So basically, it's a graphics processing unit. GPUs do a certain amount of math very quickly, but it's a limited subset. So it doesn't do everything that a regular CPU does. But what it does do, it does much faster. So inside your graphics cards, there are somewhere around 1,000 to 2,000 little tiny processors. Yeah. And they're very limited in what they do. But what they do, they could do quickly. They use little power. It's much cheaper than. So for things that work, so if you have a program that is made to be run on GPUs, so it has to be designed specifically for it, you can do that. Use that. So another question: why do you need both GPUs and processors per node? The answer there is that programs that run on GPUs, usually the whole program cannot run on a GPU. So only certain subsets of it can, and some other parts have to be handled by a core. So GPUs, the processing done on GPUs isn't smart enough, isn't powerful enough to do all the processing in your program. You basically divide, so when people write their code, they divide their code into components. A lot of the stuff that can run on GPUs is run on GPUs, and a lot of the stuff that can't is run on your regular cores. So you would need to ask for a certain amount of both, or you can ask for a certain amount of both in your usual use of a GPU, if your programs support that. This would give us 6 GPUs. It would give us 3 GPUs and 4 processors on node 1, and another 3 GPUs and 4 processors on the second node. So another resource that you could be asking for is software license or generic resources. So sometimes not only a cluster hardware is required to be scheduled, but other resources such as software license, telescope, or instrument time, something like that. In this case, you make a generic resource or license. So here's how you could be asking for a MATLAB license on Jasper. You're asking for 2 licenses for MATLAB. So if there's a limited number of MATLAB licenses on the cluster that are available, this will make sure that only, so if you have only 100 MATLAB licenses and you have 4,000 cores in a cluster, this will make sure that you only use, it only schedules your jobs to run when there's enough MATLAB licenses for your jobs to run. If you don't do this, there may not be enough licenses when your program starts, when it's scheduled, for licensed software. And you can actually see the list of software license with the job info -n command. So, oh, that's oh, it's not showing up on Jasper right now. I'm not sure why not. Or, but the software licenses show up with the job info -n. Usually at the end of the nodes. So a job info -n shows you the resources available on a cluster. It shows you each cluster node and how many cores are available. And at the end, it usually contains all the licenses. And so I was asked, does MATLAB limit the number of cores processors per license? Yes, MATLAB does limit that. So usually software that's commercial, they could either have a site license, which means that you could use it all on the cluster, or they limit it per what's it called, per core, for instance. Yes, unfortunately, the licenses aren't showing up here. So the cluster isn't reporting any of the license information. I'm not sure why.
Not working right now. Not working right now.
Okay. So yes, usually it's talking to the license servers and actually asks how much licenses are available right now. And it's usually one core is available for 1 MATLAB license. But right now, the MATLAB license scheduling and the license scheduler isn't talking. So the question is, what does drained mean? In this case, when you're looking at each node, running would be, there's processes running and there's some available. So if you look at the very top, it says processors here. There's state and processors. There's 1 available here out of 8. So there's jobs running on that machine. Busy, of course, means that there's none available. And drained means that we've turned it off, probably because it was damaged or something like that, and we're not scheduling towards that. When we were creating the test cluster, we stopped scheduling to those machines, and they were draining and then drained. OK, so we have a question. Is there a list of licensed software on the web page? Yes. There is a list of licensed programs provided in a link. What's it called? Not all the software there is limited license. Most of the software there is licensed per site. So you could use any of that software that's running there. There is a few, like MATLAB, which are licensed per core. So basically, here's the PBS script commands that you could refer to, and we could break for practice. I believe it was point 17. Jobs and memories. You could start at question 17 in our worksheet, and we're dealing here with memory. So anybody who has any questions? So you're going to start with a file called startmem.pbs. Oh, whoops. That's not the one. There's the one. There's a link to the workshop scheduling worksheet. So we have more time in this session here. You should also be able to find the worksheet inside the presentation.targ if you want to copy it over to your machine. To unzip the and you should be able to see the online worksheet. Oh, there we have somebody pointed the link to the exercise worksheet. basically the exercise number 17 through 19 show the difference between PMEM and MEM and why it's really important to make sure that you know the difference. Yeah, that job was finished already. And in this here, we see we're using 3,000 megabytes per process. Okay, somebody says after they submit, they see Q subscript written in DOS Windows text program. What does it mean? Is it an invalid format? So if you move files between Windows and Unix, they don't quite write the files the same way. There is a command called DOS to Unix, but a text file in Unix and a text file on Windows is not the same thing. If you run DOS to Unix on your Windows text file, it should change it into a Unix one. So I was asked, is the mem inside of checkjob what it has used or is using? Actually, this mem here, this part of checkjob shows what is requested. We'll go on this later, but you can actually get a lot more information from checkjob. Oh, well, if we have a job which actually is running. And you could actually get what it's using, what's requested, and a whole bunch more information. Where can you ask what is used and is required? You could look it up in checkjob. There is another command called qstat-f, and your job ID, it looks similar. You could also get emailed the results of how much memory your job has used. qstat-f. You could also add -b's for more verbosity, much more information. So in here, we actually see the differences in the memory required in the qstat-a. So you see that when you changed the amount of memory, it changes. So a PMEM of 12,000 may not run because it's asking for 12 gigabytes per core. If you ask for a memory of 12 gigabytes, that means it's used by all the cores. And if you ask for 3,000 megabytes for each core and you have 4 cores, that's exactly the same thing. In this case, your job's asking for 3,000 megabytes per core here. And here you can see how it shows up in Q step minus A. In show queue, see there's no memory here. And job info minus J. You could also do a check job. But as you can see here, there is some of the memory that's shown there in the Q step minus A. Oh, actually, we have a very good question here. So if you specify memory using a Q step minus L PMEM, does this override your pound PBS PMEM in your job submission script? And that is correct. So whatever you ask for on the command line will override the settings inside your PBS file. That's true for PMEM, it's true for cores, for anything. Yeah, my jobs are finished. You should also be getting emails back if you changed your jobs so that they email you. If we continue on for question 20, this is about jobs in memory. There's actually a program called Cryptic that you have downloaded in this directory. You don't know how much memory it requires. So the idea here is to see if you could start a job and make it run. So you have startmem2.pbs. This is a program. It asks for 4,000 megabytes of memory to have Cryptic run. It will not run. It will actually run out of memory. It will actually need more. You have to, in this example, ask for more memory, figure out how much memory Cryptic actually needs to run, and then run it the next time with an appropriate amount of memory.
Well, I'm supporting it. I'm not sure what's going on. Should we start it? No. Do a tail. Oh, it hasn't started yet. It's still, yeah, it's still, we restarted it, it's still going through and creating. How many jobs were there? I can do a
So we have some people running Cryptic already.
um, but it's still.
So here, job 1801 is using the 4,000 megabytes. It's going to fail.
Yeah, still starting.
So this is the process that you do run when you have a new program and don't know how much memory you need. We're going to have a lot more time today to finish these exercises. Today's class is not going to be as packed as yesterday's. Do you have any questions?
Okay, now try to show two. Can't make anything. You take that? Yeah. What I do?
So do you have any other questions? So, we have some extra TAs in this class as well. So even if I can't answer all the questions in the group chat, there's analysts that can answer. So we have a question. So what is the best way to iterate through this problem and assess how much memory you will need? Basically, it's to ask for a lot more memory the first time, especially if you're having to run a program many, many times. You could ask for a lot more memory the first time you run it. Just run it once instead of a lot of times. See how much memory it uses. So it'll report how much memory it uses in an email that you get sent, right? You should be getting an email. So when we did one of these, remember from yesterday that it sends you an email after it's complete. Or, sorry, when it ends, before it starts, and when it aborts. So you should be getting emails about how much memory does your job use. You can also do a qstat -f. It will actually tell you how much resources are being used right now. So you don't have to iterate it. You just have to make sure that you use enough memory. In this case, 3.4 megabytes.
Oh, in the SFT.
I think, yeah.
Yeah, on the SFTP.
Sorry, 3.4. So question, can you extend the memory of an ongoing program that you are running, or once you execute it, is it set? So you can't change the amount of memory that's available or the wall time. Because if you were able to do that, then people would abuse that situation quite a bit. You could see people extending their jobs, ask for 30 minutes and then run for a month. We can, but we have to, in order for this to happen, we would have to catch it in time and actually do a change. Okay. Is everybody done? Question 20? Does anybody have any questions? If anybody is done, please answer in the group chat if they're done, or if they're not, if they need some more time. If anybody is not ready to go on, please tell me. Okay. We'll go on to some more scheduling. So this is some more of the more advanced stuff. So job submission requiring full nodes. Sometimes there's a need for exclusive access to guarantee that no other job is running on the same nodes as your job. To guarantee that the job will only run with nodes with other jobs of your own, you can add this line here. PBS minus L and access policy equals single user. That means that on that node, only your jobs will be running. It will run on any node with either no jobs or only ones from your job. To guarantee that the job will only run on nodes with no other job, you can do an access policy equals single job. You could also guarantee that each part of the job will run on a separate node without anything else running on that node. And that's an access policy equals single task. Now, this can be used for debugging to make sure that other people's jobs are not affecting you. However, you will be charged for all the resources wasted. That will be set as resources used by your group and then used in calculating your group's priority further on. So this is using resources, and it will be accounted for like that. On the other hand, this will allow you to debug problems. This way you could guarantee that your job is running in isolation and is not being affected by anything. If it still crashes, you know it's not other people crashing your job. So another more advanced one is job submission using multiple projects. If you are part of 2 different WestGrid projects and are running jobs for both, you need to specify the accounting group for each project so that the correct priority of the job can be determined and so that the usage is charged to the correct group. So if you're part of 2 different teams on WestGrid and you need to account for the usage properly, you could specify this and then the accounting group. We'll talk about accounting groups later, but you could specify what it is. And you can find out your accounting group looking at the WestGrid portal. And you could see more information at the job info -a. So we'll come back to this later in Friday. So job dependencies. If you want one job to start after another one finishes, you can use a job dependencies. In this case, Q sub minus W depend equals after OK, so after the first job ID and then the second job ID. This means that job 2 will start after job 1 finishes successfully. So if one can break apart a long job into several shorter jobs, then the shorter jobs will often be run faster. This is also the technique to use if the required job runtime is longer than the maximum wall time on the cluster. So you could use the following little shell. You could submit your job, and that will return you job ID. You could set that to that variable, and then use that to submit your second job. So there'll be examples on how to do job dependencies. Starting one job, and then starting another one to wait until the first job finishes completely. So some of these are more advanced scheduling techniques. They could be used to make you quite a bit more productive. Prologue, epilogue, and data staging. Okay, so there are scripts that can be run before your job starts or after your job finishes. You can actually have a script and have it run before or after your job. So prologue would be before, and epilogue, of course, is after your job finishes. They may take up to 5 minutes. These scripts are nice if you need to document some more information about the state of your job in a scheduling system. Some people have created really fancy epilogue scripts that take the output of their jobs, look at it, and then have the job resubmit itself. Continue running. You can also ask for resources used. So there are special variables, $1, $2, $3, and so on, that have extra information inside your epilogue script. You can have an epilogue script that writes that information out. And based upon this output, if you wanted to, you could do very many fancy things. If you're a Unix guru or have need to do these fancy things. So temporarily available local storage. So some software like Gaussian needs to write and read many small files on a disk. The cluster, in this case, the Lustre file system, cannot do this well. Oh, okay, we have a question here. Would you need to cd PBSO work there in the epilogue script? The answer is no. And you usually wouldn't need to do that. Yeah. Okay. Getting back to our topic. So temporary available local storage. So Gaussian likes to read and write a whole bunch of small files. This can kill the shared file system between many nodes, but the local file system can be written. So each node has a local disk that is shared by all the jobs running on that file system. You can actually request to make sure that there's enough space in local storage with the following syntax. So there is a directory created for each job when it is run. When the job is finished, that directory is automatically erased. This directory name is stored in a variable called tempter. So you could go cd tempter, which is change directory, and then directly into that directory that's created for you. You can run your job. One thing that you have to do is you have to copy your files that you wish to save back into your home directory, because this directory is temporary space and will be deleted every time your job is run, after your job finishes running. So if your job needs this kind of resources, you could utilize it this way. So here's an overview of all the new PBS script commands we've come through. Oh, one thing I haven't mentioned, it's possible to ask to do really complex things. Ask for 5 nodes with 12 processors per node and 1 node with 1 processor. So there's lots more even fancier scheduling stuff that most people don't use, the vast majority don't use. Remember the PBS environment variables that you could look through inside your job as well. And we can break for practice right now. So inside the worksheet, we have a number of questions. I don't think you'll be able to run question 21 because the software license part doesn't work. You could look at the answer, though. So this is the way we would ask for one MATLAB and one statistics toolbox license, if that was working. And we're going to be doing question 20 through to question 28. This shouldn't take too long. It's just asking for different types of different ways of asking for resources, right? Trying to make sure that your job doesn't run on any nodes with other users and so on. So a question, can you run more than one epilogue script? No. You can run one epilogue script, and it could run up to 5 minutes. It will be killed at the 5-minute mark. Yeah, I don't see any jobs. So after we do these exercises, we're going to be finding out how all these commands work in detail, about how to look what's going on with your jobs. Do we have any questions?
When you do the job dependencies, can it pass information from one job to the next?
Usually what you would do with job dependencies is you would have one job finish, write out a file, and then have the second job read that file when it starts. So that way you can pass information. Is there any questions about any of the material? Or any scheduler questions in general? So here on the cluster, we have an example of job 1820 waiting until 1819 is run. So one is in state running, and the other one is waiting. Okay, so question 22, how do you see which node you're running on? That's very simple. Do a check job. Look at the check job and see which nodes you're allocated. So this job is running one processor on node CL2 228, one on node CL2 and 226, one on 225, and one on 224. So it's just allocated nodes, and then it gives you a list of all the nodes that you're allocated on. Okay, so we have a question from Damon, who says he thought he requested 4 nodes, but he only sees 1. 1817. So this job has completed. Get some more information on it. Right. So for the answer for question 222 was to submit a job that asks not to be run on any nodes with other users. Right? And you asked for prox equals 4. You didn't ask for 4 nodes. You asked for 4 processors running on any node or any combination of nodes. Also, it's possible if you ask for even 4 nodes with 1 processors each, these are treated as virtual nodes, so it's possible that you will get 3 processors, well, each on 1 node and another one somewhere else. There's ways of making sure that your request actually goes onto 4 separate nodes, but very few people use it. And I didn't think I should be making this talks even more complex than they are. So we have a question about I got flags restartable and proc specified. Do we know which job that was? Okay. So yes, restartable means that there's for instance, if our clusters are not set up to do this, but say we're going to have an outage, say we've lost all cooling in a data center and our machines are overheating. It's possible for us to actually stop these jobs, requeue them, and then see if they could be restarted. So by default, jobs are restartable. Yes, your job 1826 has run. And there, we can see its state has completed. Sometimes you may have to, if you do a check job in between the time the job is running and the time it's actually completed, it may not come back. But if you wait a couple seconds, you'll get the running job information, or the job having already run information. So it says it's completed, tells you how long it ran. And so on. Not all of you will be able to see everything about other people's jobs. What's it called? The analysts and sysadmins can. But you can see information about your own job. Oh, somebody can ask, how come I can see the job status of somebody else? You can see the job status of somebody else, but you may not be able to see a lot of the internal information for that job. So you could see what other jobs in the queue and their names of the people that are there. I think Hua. So you're saying you could see the job status of one user and not of another. Is one of those users in your group? Or are you trying to use different commands? Because you're allowed to use qstat -a to see when you run qstat -a, you should see that this user's job status is queued and that these are completed. Maybe it was just the time you were running these things. But this line here, this column right here, that's the status. So Q is for queued, C is for completed. I think we will continue on. So we're going to be continuing on, and we'll talk about how to get information about your jobs. So that's what we're going to do for the remainder of today's session. There are a few questions, but mostly they're questions about you running some of these commands while jobs are running and looking at it. So we've seen some of this stuff before. Job info -j is one way of looking at your information. qstat -t -u and the username. That'll show you job array information. qstat -a shows you all the jobs in the system. -r shows you the running jobs. Show queue also shows you a lot of information. It shows you how many jobs are active, how many jobs can be run, how many jobs are blocked, which means that they can't currently be run. Q-stat-F gives you more detailed information. Same with check job. And if you add -V to check jobs, you'll get a lot more detailed information. So we'll go through some of these commands. When you do a job info -J, you have the job ID. This is the job number. We have the state, so like running, idle. We have how many processors does the job need. We have the wall clock limit, which means how long this job is the maximum amount of time it could run. We have the username, and we have the class of the queue. We have other things such as we could be requesting like features. Q-stat-T -U username, so that will give you jobs inside a job array. So especially if you have a large one. In here we have, a pretty big job array from 349 to 356 here. Some are queued, some are running. And you can see a job name here. Other information here are number of nodes for each job and the number of tasks, processes, the required memory, and the required time for this job to run, as well as its state and how long it's been running. Are there any questions? So here we have Q-stat-A. Once again, job ID, username, sometimes the queue. There's multiple queues. Here's an example of different queues. The job name, different jobs. How many nodes? What's the required memory? How long can the job run at most, and how long it's been running, as well as its state. In this case, running and queued. Q-stat-R is like Q-stat-A, but it only shows running jobs. So let's go to an example of show queue. Show queue is a nice command. Sometimes it takes a bit longer to come back. It shows you running jobs and active jobs here. As you can see the job ID, the user who's running it, the fact that it's running, how many processors it uses, and how much time is remaining for the job, and when it was started. Other information is that here we have 640 of 2,048 processors are used by local jobs, so just a few. Of that, 80 of 256 servers. We also have jobs which are eligible, so these jobs can start running if there's enough space. So they're in state idle. We have other jobs that are blocked. In this case, it's deferred. So we'll talk more about this in a talk tomorrow. But if a job can't run and tries to run and it fails to be run, maybe there's an issue with the job or the node, it gets deferred for an hour, then it's tried again. Show Q minus B shows you blocked jobs. There could be multiple reasons for blocked jobs. Jobs could be deferred. After they tried to be deferred for a while and they can't be run, they'll go to batch hold. Sometimes they can't run because the user is already running a whole bunch of jobs. So they may be in state idle, but they still can't run. Are there any questions? Okay. Show Q minus I is interesting, or job info minus I, because it tells you your priority. It lists the jobs by priority. So we only have one job right now, and it has a negative priority of 46,831. If there was more jobs in the queue, it would list jobs in order of priority. So who has the highest priority job? And this will tell you roughly when your job will run. Or it could inform you towards that end. You can look at the output of the qstat minus f command, and then your job ID. It'll tell you your job name. It'll tell you your job state, in this case queued, your queue, in this case parallel, where it's going to send any error messages, whether there's any holds on your job, preventing it from running, say because you have a dependency, if it'll email you your email address and so on. Also tell you what type of resources you've used or you've asked for. What happened there? The output path, your job's priority, whether you've submitted it with any arguments. Check job also gives you a lot of information as well about your job. Your username, your group name, your accounting group, the queue that it goes into a class, how long it's been running, in this case 0 of 3 hours, when it was submitted, when it became eligible to run, how much of the time has it been queued. This means it has been queued for 20 minutes in a queue. And you actually gain priority for sitting in the queue for a limited number of jobs per user. So this job is eligible for that priority gain for sitting in the queue for 20 minutes. And how many processors it uses tasks? Here is 12. How many resources per task? So one processor and quarter of a gigabyte of RAM. When I'll be notified in my email address, what was the start priority when my job started? Minus V gives you a lot more information. Used resources per task. We'll talk about features later and node sets. You can do it that way. That will be talked tomorrow. You can see what the output files are, what environment variables. So this is what we, as sysadmins and analysts, use to debug your jobs. So when you say your jobs have died or are having issues, we look into here and use it to diagnose the problems. Check job minus V. If your job is not able to run, it will actually tell you why it's not running on every single node. There'll be a lot. And sometimes it would say at the end, cannot run in partition because there's not enough empty processors available. Maybe there are enough processors available, but not enough processors with any RAM, with enough resources to run your job. Or it will say that it's not going to start this job until your other jobs start. So it only checks a few jobs at a time. We'll discuss that tomorrow. So we'll look at a cluster. Yeah. Actually, do we have any questions? Okay, so a quick question. So somebody's asking, they have 1,000 simulations. What would be the best way to do it? Submit as one job or divide it into a whole bunch of different jobs and so on. So the best way to do it depends upon how big your simulation are. How long does it take to run a simulation? If it takes 10 minutes, you may want to, okay, so suppose 4 hours for each simulation. How many resources would you need? So is it one core, or does it require 1,000 cores, a lot of RAM, or not? Based upon how long each simulation runs and what type of resources you would probably run it differently. If it requires 4 hours each, you can, and a large amount of memory with one core, you could create an array of job, one for each. You could read an input. So this would be exactly like the way we did, I think it was question 10. Yeah, yes. So we gave an example of how to run an array job taking input from a file. So probably an array job would be the most efficient in that case. If they were only taking a few seconds each, you'd probably want to batch them up into one job. If they were taking much, much, much longer, you may just want to run each of these separately. Look at the outputs and run the next one. Yeah, so an array job in this case, if you have a 4-hour simulation with one core each, would probably be best. It's probably the easiest for you to organize your workflow, and it's easiest on the system. So to demonstrate some of these commands. Use that -t here, showing us each task of the array. Oh, yes, I am sharing my screen. Can you guys not see my screen? Okay. Good. So one of the best commands, of course, is check job. And you can see very much information out of it. So here's one for I think that's question 20. Running on one node. So yeah. So are there any questions? Oh, okay. So there's a question. So when we run the job in question 10 as an array job, what is the job ID? Okay. So some of these are referred to the job ID like this. This refers to the whole job. This refers to the piece of your job, I guess. So no, you can do a check job. On that piece, but you can't do it on the original job ID. So this is the check job on job 1832-1. So job IDs are a bit weird when you look at array jobs. And yes, so check job it without the CL2 and 231 extension. So inside a worksheet, we do have a few questions. Most of these are just you're running a few jobs and then looking at jobs with the job info minus J or the qset minus T commands. Looking at this cluster. You may want to actually log into the actual Jasper cluster itself. When you do a qset minus A, you can see quite a few jobs on Jasper. All kinds of information here. Notice that the job IDs are much, much higher. So we're almost having 10 million, 9.5 million job IDs have been processed by Jasper. So some jobs, as you can see, use a lot more RAM than others. A lot of these are queued. We can see a whole bunch of block jobs here on Jasper. We can see jobs batch hold. These jobs are having problems running. Other ones usually just have a very large number of jobs. and these jobs are waiting until other jobs start running. It's job array jobs. Let's see if we can find a job, somebody with a job array. No, I don't see any job arrays in use right now. Job arrays are usually superior to putting a very large number of jobs. Some other users find it annoying if somebody puts in, 5,000 jobs, which are identical, where they could have just used a job array and saved themselves trouble as well as other users having to page through a large number of jobs.
I can also find this on
You can see show queue. You can see running jobs of different types on a large cluster. Pages and pages of running jobs. Jobs that can't be run right now. And then jobs that can't. Show queue minus I is nice on a real cluster. Or job info minus I, which is the same thing. You can see people's priority, jobs priority for each type of job. So you can tell where your job is in the priority queue. Of course, that all changes as the situation on the cluster changes, as your use and other users' use of the cluster changes, as new users submit jobs and other jobs finish early. So we could do a question. So break for practice. All the way up to question 30. Do we have any questions? Any questions at all for the last 2 days of talk? So question, can you have the start of one job be dependent of more than one job finishing is the job dependencies line? I'm not sure. I mean, it's possible to have job C wait for job B to finish, and job B wait for job A to finish, so that your jobs run A, B, C. That's possible. You don't even have to set. You could just ask for job C to wait until B finishes, and job B to wait until job A finishes. Not sure whether you can do that. Add more than one dependency. So if you guys need more information on how this stuff works, you can look into the adaptive computing website, where they have a lot of documentation. about these commands work, how these systems work, and so on. But be warned, these are thousands of pages documentation. Okay. So I've been informed that you can give multiple job IDs for a job dependency. I haven't tried that myself, but it's possible. Are there any other questions? If you want to clean up your directory, get rid of all the answers, you could run the little script that I have to clean up. Also, with these running jobs, I wrote a little run info, which actually shows you, just basically runs the show queue minus U, the Q step minus A, the Q step minus T, and the job info. Any other questions? So tomorrow we're going to be discussing how priority works. So, who gets access to when they're running, how you could see the state of the cluster, and how do you find out when there's something wrong with your job. So there'll be a few exercises there, and a lot more understanding upon those topics. Any questions? So we'll stay online here if you're having any questions about any of the exercises that you may not have had time to actually complete. Thanks, everybody.
Thanks, Kamil. I think that was another good session.
Yeah. Well, this one was more sized correctly, I think, to the work. Yeah.
Well, and there's always, as you said, there's always that rough start at the beginning.
Yeah. Well, we promised to be here till 3:30, right?
Yeah, so 10 more minutes.
So yeah.
I guess I could have left a few more minutes in the exercise portion.
So tomorrow will be sort of the first time you've done part 3 as its own session too, right? So that'll be interesting to see the timing for that.
Yeah.
Hi guys, it's Garth here.
Hi, guys.
Hi.
You reading me? I just popped back in here. Are you done for today? Is that right?
Yep.
For this session?
We were just staying online until, technically it's supposed to go till 3:30, so just in case anyone had a few last questions, we were going to go right up to the half hour.
I
but,
see. Okay, sorry. Excuse me for the interruption then. Should I stop the recorder now or should we wait for a few minutes? We're just headed out to a meeting, so.
I'd say stop, because that's fine. All the sort of content is done, and
Okay.
so if you stop the recorder, then I can hang up the call.
Yeah.
Sounds good, and I'll just stop the recorder now and you guys can go on with your meeting then.
Okay, thanks so much, guys.
Thanks. Okay, bye.
Bye.
Bye.